My name is Sean Kramer, and today I will be presenting an in-depth look at memory safety in C and C++ executables. When examining the C and C++ languages, it is apparent that they both suffer from vulnerabilities stemming from memory management. The easiest solution would be to ignore these languages altogether, but with the growth of embedded devices and the Internet of Things, these languages are more popular now than ever before. Resulting from this growth, attackers have a new domain of programs they can target, and the lack of memory safety allows them multiple entry points to cause corruption. Countermeasures do exist, but have serious drawbacks that prevent them from being widely adopted in industry. More on this to follow. With that in mind, the goal of this work is to implement complete memory safety at the executable level, meaning that the source code need not be present to provide a reliable countermeasure. Our approach is to utilize a static binary rewriter in cooperation with the low-level virtual machine compiler infrastructure. Our goal is to disassemble an executable to a human-readable representation where we can then identify variables, data types, and function prototypes and implement a memory-bound checking countermeasure to thwart attacks on programs' memory. To understand how memory safety should be incorporated, we must first recognize and differentiate between the two types of memory access violations: spatial errors and temporal errors. Both spatial and temporal errors are caused from dereferencing a pointer, and depending on how the pointer is dereferenced correlates to what specific error has been targeted. Spatial errors dereference a pointer to outside of its allocated memory space. For example, in the bound checking code snippet below, the pointer P is forced out of bounds by setting its value to the memory location just beyond the allocated space of the array instruct S. Temporal errors dereference a dangling pointer, which are pointers that do not point to a valid object of the appropriate type. For instance, if a memory object is created and its location is given to a valid pointer, when that object is destroyed, the pointer becomes dangling. Another example can be if a dangling pointer points to memory that has already been freed, the storage is no longer allocated. Trying to access this allocated space would cause a segmentation fault. By taking advantage of memory violations described, there are four categories of attacks that can be carried out. The first, code corruptions attacks, as implied by its name, look to corrupt code by overwriting the program in memory. Control flow hijacking attacks modify a code pointer to cause the program to deviate away from its intended flow or to relinquish control over to an attacker. These types of attacks are of utmost importance as they are considered to be the most common type of software attack in existence today. The next attack is a data-only attack, which looks to modify the program's logic in an effort to gain more control or access higher privilege levels of a system. And lastly, information leakage attacks function to leak memory contents to gain information about the system. Oftentimes, information leakage attacks are used in conjunction with other attacks, as the attacker must learn about the functionality of the system or program to find its vulnerabilities and entry points. Building off the last two slides, the image shown here is an example flowchart describing how memory violations can lead to the various attacks. At the top level, we have spatial and temporal errors, each caused by dereferencing a pointer. That pointer can be used to either write to memory, read from memory, or to free a section of memory. How the dereferenced pointer is used correlates to the specific type of attack category, with the exception being the modification of data pointers, which are utilized for the purpose of creating another spatial error. Now that the attacks are understood, let's look at why current safety features have not been accepted. The major problem with a majority of these techniques is that they are incompatible with legacy software, and oftentimes the source code must be made available or modified in order to fit in with the security procedure. Hardware-based solutions are accepted for their low overhead implementations, but suffer from a lack of effectiveness and incompatibility. Software-based solutions can be implemented at the source code or binary levels. At the source code level, existing countermeasures can provide a complete protection against spatial errors, but cannot stop temporal errors and accrue a large overhead. Binary rewriting solutions also exist, and they have the benefit of not requiring the source code to be present, but they also suffer from large overheads. In fact, some procedures require a copy of the unmodified binary to remain present somewhere in the new file, causing an overhead of at least 100%. Here is a figure documenting the existing LLVM compiler and how our approach will be integrated into this architecture. During normal compilation, the input file, a C or C++ source code, is transcribed from its source code format to LLVM's intermediate representation, also known as IR. IR is a machine-independent assembly language that utilizes an infinite amount of registers. The IR code is then run through optimizations, known as compiler passes, and output as a machine-dependent assembly language, where the assembly language is specified by the target architecture. In our approach, we wish to begin at the executable level and transform the binary code back to an IR representation. From here, we can run our own custom compiler pass to extract relevant information and implement the bounds checking security feature. The optimized IR is then sent back through the machine-dependent backend to output a modified binary that will still retain normal functionality but be integrated in with our countermeasure. So let's take a look at exactly what IR code is. On the left is an example Hello World C program with a local variable x created and initialized to the value of 6. After being sent through the Clang compiler, we see the output IR code on the right. The gray box within the IR code file is specifically the main function of the code on the left. Notice the lines that are highlighted in red, as they directly correspond to the creation and initialization of the local variable x. In a successful disassembly to a similar IR format, our ideal output from the disassembler would be akin to the code listing on the right, where variables and data types can be easily distinguished. In order to get back to an IR format, we must first correctly disassemble a given binary, something that poses many problems. The one large problem is that function entry points are difficult to interpret, especially in the case of stripped binaries where symbol information is unavailable. And even if the entry point is located, indirect control flow transfers can disrupt the disassembly process. Another problem that arises is the differentiation between bytes that are code and bytes that are data. Oftentimes, data bytes are interpreted as code, and code can be misinterpreted as data bytes. There are two tools available that can help expedite the disassembly process. Dagger is an open source binary translator to LLVM IR. The benefit is that it integrates directly into LLVM's infrastructure, but Dagger is unable to identify external function calls, and the IR produced does not come out as clear as the code listing shown previously, making our task of extracting information much more difficult. The other option is the Capstone Ultimate Disassembler, which is another open source tool, which instead of producing an IR code, the disassembler can transcribe bytes as machine-dependent assembly instructions, and the infrastructure of the disassembler can be programmed or modified using C, Python, or Java.